Good morning friends. Up till now from the last two series we have discussed the part of statically determinate beams and we have started shear force and bending moment diagrams. From last two sessions we have studied what is shear force, what is bending moment and how to calculate the shear force and bending moment at a particular point. In the previous session, we have also solved certain numericals based on shear force and bending moment diagram. We had drawn bending moment and diagrams, shear force diagrams for specifically statically determinate beam. The name of the beam is simply supported beam with point load and UDL, as well as the combination of point load and UDL. Today now we are going ahead with the next more typical problems solution with the combination of loads for statically determinate beam, specifically simply supported beam using uniformly varying load as well as action of couple and the combination of load. So now let us go ahead with the next problem. Before I will proceed further for the plotting of shear force and bending moment diagram, let us recall certain important points, certain issues. What is shear force? Shear force is defined as algebraic sum of the forces to the left or right of the section. What is bending moment? Bending moment is defined as algebraic sum of the moment of the forces to the left or right of the section. Based on these fundamentals, we had drawn certain SF and BM diagrams for simply supported beam for point load as well as uniformly distributed load. The same series, this given beam of length of 6 meter subjected to uniformly varying load 0 at support A and maximum 10 kilonewton per meter at support B. So now let us recall what is our first step right now. The step number 1 is the calculation of support reaction, because support reactions are the basic unknown that we have to find out first before plotting of shear force and bending moment diagrams. So let us start the next one. Now please see the figure. This half into 10 into 6 is the equivalent point load which will acting at the CG of the triangle. So what I did over here, I have converted this triangular UVL load into the equivalent point load, that is half into 10 into 6, half into maximum magnitude multiplied by the length of the beam, which will act at the CG. The CG distance from A is 2/3 of 6, that is of 4 meter. Now let us apply the first equilibrium condition, sigma h is equal to 0. So at the A junction, as see the previous figure, previous slide, the A, that is a support, the name of the support is the name of the given support is hinge support. So here there are two unknowns, horizontal reaction, vertical reaction. At the B there is a single unknown, that is the vertical reaction. So over here the two unknown RAH and RAV. So if we apply the first equilibrium condition, that is sigma h is equal to 0, the RAH value is equal to 0. The reason behind is that there is not a single horizontal force which is acting on this particular system. If we go for sigma V is equal to 0, sum of all the vertical forces which are equated with 0 with this condition, then all the upward force which are equated with the total downward force. As per that, RAV upward and RB both are upward, hence plus is equal to total downward load, that is half into 10 into 6, that is the 30 kilonewton. So this equilibrium condition sigma V is equal to 0 gives us an equation having two unknown, that is RAV plus RB is equal to 30. So we have right now two unknowns, and our intention is to find out these two unknowns by using now third equilibrium condition sigma m at any point is equal to 0. Right now let us take sigma ma is equal to 0, sum of the moments of the forces at point A is equated with 0. Hence, if we apply the moment at point A, the first force RAV into 0, because perpendicular distance is 0, while another force half into 10 into 6, this is the equivalent point load, creates a moment at A, half into 10 into 6 multiplied by 4. This creates clockwise moment. So plus sign half into 10 into 6 into 2/3 of 6. This 2/3 of 6 is nothing but the 4. And it creates clockwise moment, hence plus sign. Another force RB creates anti-clockwise moment. So RB into 6, so minus RB into 6 is equal to 0. So by simplifying this simple equation, we will achieve the value of RB as 20 kilonewton. By replacing the value of RB in above equation, this equation RAV plus RB is equal to 30, we will replace the value of RB as 20 over here. We will achieve RAV as equal to 30 minus 20 is equal to 10 kilonewton. So now using the first step, we are able to find out the important parameters, that is the unknown parameters, that is the support reaction. Now next intention is to plot shear force diagram. Let us go ahead with the next one. Now let us plot over here. This is my given beam. This is of 20 kilonewton, 10 kilonewton, subjected to UVL, now start with the drawing of the baseline. Here the given load is of UVL, uniformly varying load. Up till now we have solved the problems in which the load acting on the beam is of point load as well as UDL. So we know how the performance, how the shear force diagram, we can plot it out. But now here the UVL is there, so let us go our original method by taking a section. This is the joint A, this is the joint B. As we know, the shear force at A is equal to nothing but its reaction itself, that is of 10 kilonewton. Question about the sign convention, plus or minus. Then if we take a section over here, section left upward as for our sign convention it is treated as positive. This is the positive sign convention. Now if we take section shear force at B is equal to its self reaction value 20 kilonewton, about the sign convention, if we take this section right upward, this will treat it as negative. So we know the value of shear force at A and B, but we do not know what is the variation between A and B, and hence we have to take the section method. Let us take a section X from A and see what is the equation for shear force at section XX. So let us plot a free body diagram within that section. So I will plot a left part of a section. We do not know this magnitude and we have to find out this distance of beam is of 6 meter. This value is of 10 kilonewton per meter. So can I write down for 6 meter horizontal distance, if this vertical ordinate is of 10, then for x it is how much? It is 10x by 6. It is nothing but 5x by 3. So this ordinate is known to us 5x by 3. Now let us go ahead. Shear force at section XX is equal to section left upward plus 10 minus the downward load. Downward load is nothing but this of partial UVL. It is nothing but the area of triangle, that is half into x into 5x by 3, and that is equal to 10 minus 5x square by 6. Visualize these equations very carefully. The equations gives us in terms of x square. X square means the behavior of shear force, that is the variation of shear force along the length of the beam, is of parabolic nature. The behavior is of parabola. Now let us be found out for each and every 1 meter interval, and we found out the ordinates. So to find out that, let us go ahead. Shear force at 1 meter is equal to, we have to put x is equal to 1. So we achieve 10 minus 5 by 6. And what is the value of 10 minus 5 by 6? And we achieve 10 minus 5 by 6 is equal to 9.16 kilonewton. SF at 2 meter, 10 minus 2 square 4, 4 into 5 20, 20 by 6. So we will achieve 10 minus 20 by 6 is 6.67. Shear force at 3 meter interval, 3 square 9, 9 into 5 45, 45 by 6. So 10 minus 45 by 6. So if we achieve 10 minus 45 by 6, that is 2.5 kilonewton. And if we go for 4 meter, So we find out at each and every meter interval 4 meter. 10 minus 4 square 16, 16 into 5 80 by 6, and that is 10 minus 80 by 6 gives us the value minus 3.33. SF at 5 square 25 into 5 125 by 6. So 10 minus 125 by 6 gives us the value minus 10.83, and replace the at 6 meter, that is at B. Over here at B we will achieve it is as of minus 20. So by joining all the points, this is the 10, this value is of 20, this is the central third meter, 1 2 3 4 5 and 6, and let us put the ordinate value 9.16 6.67 2.5. so here central ordinate is of 2.5, and then it goes the minus sign. The join this all the points, this is the diagram, is known as shear force diagram, and this line is of parabolic nature. I repeat once again, this line is of parabolic nature, as this equations gives the equation of parabola. Now this point is interest. It is our intention is to find out what is the distance from A. Why? The reason behind is that our intention is to plot the bending moment diagram is also, and the point at which the shear force is 0, we will achieve maximum value of bending moment. So now the equation is there with us, that is shear force xx is equal to 10 minus 5x square by 6. To find out the value of x, I have to put is equal to 0. So